Hello everyone, I'm Shohei Mori from Graz University of Technology in Austria. Today I'm going to present our work, Exemplar-Based Inpainting for 6DoF virtual reality photos. Multi-layer images allow us to change the viewpoint in real time within a certain range. The trick here is the RGB plus alpha layers slicing over the scene to surround the viewer for the immersive experience. In this research, we refer to multi-layer scene representations as 6DoF virtual reality photos. Due to its simplicity, the rendering can be fast. We wrap individual images and composite them from back to front by alpha blending. Deep neural network is often used to analyze the scene points from input multi-view images to create the VR photos. Same as in normal images, editing is hard once it's photographed, especially for us because multi-view images and deep neural network-based compositions are involved. In this research, we particularly focused on removing things from the VR photos, that is known as inpainting tasks. Since original multi-view images might have observed some hidden parts, assigning alpha values to zeros to frontal objects can already remove objects. However, non-observed parts of course remain as wholes. Straightforward solution would be to apply screen space inpainting at every frame, but this breaks the frame coherency. There exist direct 3D inpainting approaches that fill in holes in 3D data, such as 3D texture mesh and volume data like CD data. For multi-layer scenes, there is no explicit geometry except for the proxy layers and pixel colors. Also, the layers are arranged at discrete distances from a center of projection, making image resolution dependent on the layers. Therefore, we need a specialized algorithm for us. The most closely related to our work, in terms of the underlying data structure, are methods that partly fill in the background layers in 3D layered images. However, those work extends the boundaries and do not leverage to completely fill in the holes, as you can see in the video. This is where we contribute to. Again, we contribute to 3D image inpainting. Although assigning alpha values we can already delete things, we need a labeling tool to accomplish this. After the labeling, we need an inpainting algorithm that automatically fills in the marked holes. So in summary, we present the first approach to inpaint multi-layer scene representations for hole filling. We introduce a multi-layer image inpainting pipeline that includes an interactive segmentation to expose background pixels and a multi-layer image inpainting algorithm that fills in unobserved remaining pixels. We compare variants of our multi-layer image inpainting algorithm with baseline approaches to validate our design choice. We distinguish two types of labels for object removal. One for masking and by assigning alpha values to expose the existing background, or fallback pixels like black pixels as holes. And one for inpainting. Our interactive desktop segmentation tool allows us to select one of the layers by mouse scrolling and assign those different labels like in a digital painting tool. To assist the whole selection, we sample rays within the volume to see if rays hit something or not. The labeling tool has another window that shows the current edits in real-time preview. Our inpainting algorithm is based on patch match, which finds the best matching patches from random pixel locations. The algorithm evaluates patches using the sum of squared difference. The red shallow volumes represent patches for the holes, and white pick ones are candidates to fill in the holes. So we evaluate SSD of volumetric patches. In other words, we treat the 3D image as a 2D image with very long channel pixels to avoid copying far pixels to near pixels that appear in different sizes and vice versa. Now the patches that took the smallest SSD are chosen for individual holes, and they are copied and merged with the other candidates within the holes. We repeat this process for every image pyramid level. Since existing work for 2D image inpainting has already explored different types of patch metrics, we wanted to evaluate and implement those variants for our approach. Now, our goal is to validate these variants in our 3D image setup. Since the 3D image has explicit volume, we can import conventional 3D models into the scene and show it in a VR headset, for example. In this example, we put textures 3D mesh in the scene using Unity editor. Our VR applications allows us to switch the scenes to exhibit the original masked and inpainted scenes for different scenes. This video shows our VR app running on the desktop PC with MetaQuest 2 connected via a USB 3 cable. Here you can see that the holes are filled completely now, but still the scene disparities appear plausible. To evaluate our approach, we conducted a user study where the participants evaluated the inpainting quality in 7-point scale on the web form. To enhance the disparity in 2D screen, we moved the camera in the synthesized scenes. In addition to our variants, we prepared 3 more reasonable baselines. Multiview CNN performs Deep Field V2 on every input multiview image and then generates a multi-layer image. Multiview Photoshop replaces the deep neural network part of the multi-view CNN with a Photoshop content-aware fill of a commercial de facto standard. Per layer patch match implements per layer RGBA patch match. So, in the end, we hypothesized that our SSD plus patch flipping and intensity compensation would perform the best. Second, simple masking with our labeling tool would perform the worst. Third, per layer patch match would follow the second worst because it ignores coherence across the layers. And finally, our variants would perform better than multi-view and per layer approaches because ours can take the volumetric information into account, and the others would miss coherence over the input views or layers. Our results supported hypothesis 1 and 2 and hypothesis 3 and 4 only partly. What we found was that per layer patch match is the second worst, but content with multi-view Photoshop. And ours outperform multi-view Photoshop and per layer patch match, while no clear superiority over multi-view CNN. So, in conclusion, we proposed the first multi-layer scene inpainting method and pipeline for hole filling. The pipeline includes acquisition of input multi-layer image, a semi-automated labeling tool of the region of interest, and a new exemplar-based inpainting algorithm for multi-layer image, and VR viewing of the inpainted results. Through the user evaluation, we found that the combination of patch filling, flipping, and intensity compensation helped the most. Thank you for your attention, and we are happy to discuss our work.